So let's start. Okay, so let's start. So welcome back, everyone. Now we have Katrin Heitmann. I hope I pronounced it. Who will tell us about cosmological simulations for large-scale sky surveys and the LSST DESC data challenge.
Okay, this is good? Yeah. Well, before I start, I quickly want to thank the organizers who are now, is Antonino at least here? Yeah, so I was a tiny little bit worried when I came here because it's a huge city and I don't speak the language and I often get lost in places and if you can't ask where to go. So, but you guys took so great care of us. It was really, really nice. Thanks a lot. It's really great. This talk is a little bit different from most talks that we heard during this week. It's kind of like an infrastructure talk. It's not finished. It's work that's going on for like 14 months, something like this. And I really had hoped that I would show you the final results when I signed up for this workshop, but we'll see some results. I am from Argonne National Lab. For those of you who don't know where that is, it's close to Chicago. And I'm here today to talk on behalf of the DESC collaboration. And I am the simulation and computing coordinator in DESC. And when I signed up for this job a little less than 2 years ago, one thing I didn't think about is that LSST doesn't have data right now, so simulations play a really big role. The other thing that I wasn't aware of was that simulation and computing coordinator also includes thinking about data management processing. So I am not an astronomer, I'm a theorist. So when Tessa yesterday said, I'm so sorry, I'll show you an action slide, I was like, yes, an action. So I'm a real theorist. And so I've learned a lot during the last year. And you'll see some of this. And given that, the title of my talk have been also how I, a theorist, learned to stop boring. So you see me here boring, and you will see me boring throughout the talk. And really love to learn about CCDs, flats, darks, cadences, and everything that has to do with telescopes, which really had not much of an idea about. So you have seen this picture during the week already quite a bit. We are getting there. It's not an artist picture anymore, but really a photograph. So this one is from Sunday. So the thing is really getting there. And what I will show you today a lot is simulations of the LSST focal plane. So here you see the camera. The focal plane is here. And so my life in the last year really developed around simulating what this camera will actually see once it's switched on. Very quickly, the LSST survey and data. So what you see here is the footprint in red. So it will be an 18,000 square degree survey in the south. There will be deep drilling fields, square degrees deep, so 10 square degrees large. So they will go very, very low. The telescope will come over and over back to these regions. And this is mostly for the transient science. There will be worldwide alerts every night. So every night you can get up, start your own team, and follow up what LSST sees and tells you to see. This will be actually a very interesting challenge with regard to big data. Like, what do you follow up? What is interesting? Not. And people are still working on the so-called brokers. And then there will be annual data releases. So these are the things we care about when we are cosmologists. So we have images, objects, source tables. And so they will come out annually. And I think every 2 years they will be made public, worldwide publicly available. All US astronomers, all people from Chile, and many, many more people actually have data rights, so can work on the science. Oh, sorry, I forgot something. And this is the little patch that I will be talking about during this talk. So this is what we call DC2. And you will hear about everything. So DC stands for data challenge. In recent months, when I send my secretary, so at the national lab in the US means that I often have to go to DC. And when I send her an email, I send her saying I have to go to DC too. And so it told me like I'm working too much on this topic. Here's the dark energy science collaboration. We have heard about it, and it's actually funny. Each of us took a picture from a different workshop. So this one is actually from Stony Brook. So officially, we have, as of today, 864 members, almost 200 full members. You become a full member if you like sign a piece of paper and describe what you're actually to do, and somebody looks at it and says, yes, that's useful. Besides the more generic collaboration meetings that we have twice a year, we also have once a year a hack week where we get together for 1 week and just work on projects. So there are no talks. It's really just working together. And this one actually here is at Argonne, in the computing facility at Argonne. So what are the LSST data challenges? So, what we want to do in the dark energy science collaboration is actually generate simulated data sets that look as close to the real data that comes out from the telescope and then from the processing machinery as close to reality as possible. And so really we want to do an end-to-end simulation of everything. We want to include the CCDs, the atmosphere, everything in the telescope, good galaxy. So it's, as you can imagine, it's quite a challenging task. And why do we want to do this? So we want to be really prepared when the data arrives, that we have our analysis pipelines more or less ready. So we want to have data we can test our pipelines on and develop our pipelines against, and then actually see if our pipelines are working correctly. We also want to look at systematics. So you have heard this very nice talk by Elisabeth this morning, where she described what systematics we have to worry about. And so we are actually implementing a lot of them in these data challenges. So the simulations have CCD effects, for example. So we want to see if we can actually take them out. If we can't take them out cleanly, what can they do to our cosmology constraints? Blending is a big worry in LSST. So you saw in Elisabeth's talks this plot where you showed you this mush of things, which for LSST might look like one galaxy, but actually if you would have a higher resolution telescope, it would be two galaxies. And this can be a problem if you don't cleanly separate them, and you don't know how to do that. So having simulations where you know the truth, what is a galaxy and what is not, is super helpful. And then we also want to test and develop data access strategies. So the data set will be very large, and we want to make sure that the collaboration is well prepared how to deal with the data. So we are trying to get as close as possible to how the LSST data releases will look like, so that we are well prepared there as well. So the data challenges have been set up in 3 stages. So the first one was DC1. It was kind of a Pathfinder project, 40 square degrees. Just one band, R band, no weak lensing. So it was relatively restricted. So it was just for us to see how things are going and just to get started. DC2 is much more, much bigger. So it's 300 square degrees imaging. It's in all bands, all working groups are engaged. So in DC1, it was mostly focused on the large-scale structure working group because that what was the data was useful for. And the third data challenge, DC3, is currently being planned, and it's not quite clear yet what it will be. So if you want to get involved, you can still even help designing that one. So DC2 is supposed to provide a complex challenge for the different working groups, and we really try. Elisabeth listed all the 6 analysis working groups that we have. So for each of them, there's something in there. So in working groups as well as for weak lensing, large-scale structure, and so on, clusters. And so the one thing that is an interesting part of this experiment is to just see people working together. So we are a big collaboration. Communication is not always perfect. Sometimes you get overwhelmed with Slack messages, GitHub issues, Google Docs. Somebody wrote a Christmas message about, like, the question, what do you want to do over your Christmas break? And he said, I want to go to a nice place with no Google Docs, no GitHub issues, where everything makes sense, funding is great, and I get every evening eggplant parmesan. So that tells you a little bit that people are, it's an interesting experience, and I think we have to still improve on these things. So a lot of people have contributed, more than 50 people, and if I missed your name here, sorry for that. I really try to include everybody, but it's a lot of people. So it's on the design of the data challenge, the catalog production, and the validation. So what I'm not listing here is any of the science that's going on already with the data. So here's what the design looks like. So we have generated an extragalactic sky, and I will talk about that in detail because that was the part that I was most involved in. And right now it's 400 square degrees, but early next year it will be a 5,000 square degree catalog. We have a static sky with images, which will be used. So these are the acronyms for the working group: weak lensing clusters, large-scale structure, and PhotoZ. And that will be 300 square degrees in the main survey area, which I showed you at the very start. It will be the 10-year survey in all 6 bands. And so it's this wide, fast, deep cadence. So it basically the observations are not deep. So it's really optimized for the cosmology probes, weak lensing and large structure. Then there will be also a time domain part to this. So I will show you how we actually put supernovae and strong lenses into this data challenge. And so these are the so-called deep drilling fields. And that one is 1 square degree. And so what you see here is, so one thing that you see here is one of the simulated focal planes from LSST. So you recognize again this pattern that I showed you at the very start, what the telescope will observe. And here you see the wide, fast, deep region. So this is the 300 square degree region. And the thing that hops around here is actually the LSST observing strategy. We really went out there and we did look at how the telescope will survey this region. So this is super realistic. So it has to hop around like this in order to actually, so you see here, so what you see here in the focal plane are the CC, these black gaps in between. And so in order to cover all these gaps, you have to hop around and just cover this. And that's what you see here in this hopping around. Up here you see also a little bit of hopping around, so that is the deep drilling field, which just has this 1 square degree region. And so Humna Avan from, I forgot the university where she is at, but she's Erika Weiser's student. She made these plots and she put in a lot of effort to really give us an observing strategy that is exactly what LSST will do. So this observing strategy is called right now Minion. There's a huge long document that describes this. Again, it's from the LSST project where they do this. And so as part of DC2, we had a first test run, which we call run 1, which is 25 square degrees. So this is not DC1, this is really the 6 bands, everything there. But it's not as deep, it's out to Z of 1. And that overall has 8,389 visits. So a visit is one of these squares. Run 2, which will be the full DC2, is the 300 square degrees, goes out to Z of 3. And if I take together the wide, fast, deep and the deep drilling fields, it will be 75,000 visits or 7.5 sensor visits. So on each of these squares, you have distributed it into sensors. So it's actually 189. And so that's why I'm telling you all these numbers. I had no idea a year ago. If you would have asked me about LSST, I would have known nothing. So all of this stuff I had to kind of catch up pretty quickly on. And so in order to do this, in order to simulate 7.5 million sensor visits, major supercomputing resources are required. Just give you a rough estimate. In order to do one sensor, it takes 8 wall clock hours. You can stuff 32 on if you have, depending on your computer, of course, but at NERSC we have a computer. So this overall, this whole thing with roughly 200 million hours at a supercomputer like at NERSC. So 200 million hours depends a lot on what the computer is. But. So this is a workflow to generate this data set. So here on the right, and I know you can't read this, but that's okay. is the extragalactic catalog generation. So you start off with an n-body simulation, you populate it with galaxies. We have heard about that during this conference already. You get an extragalactic. Then the next step is that you use this minion 1016 cadence and you actually make everything. The other thing that is interesting to me was that in these cadence catalogs, what's also in there are observing like how high is the moon, stuff like that. So it's kind of interesting when we did test runs and validation, we just picked randomly a visit, and then somebody said, well, why did you pick the visit where the moon is almost all the way up? And it's like, sorry for that. So the visit was not easy to validate because everything was just so bright. But I thought it was very interesting that all of these details are there. Of course, also the atmosphere is in there, the how much clouds are on top of you, things like that. So you do the image simulations, and I'm going to talk about that. And then the last step is the data processing with the data processing pipeline that is developed by the project. And when the project, there is this distinction in LSST. The LSST is a project which will deliver data to the science collaboration, and so DESC is a science collaboration. This is just the same workflow in 3 pretty pictures. Here you have the embodied simulation, here the image simulation, and that's what's coming out at the end, the processing. So the extragalactic catalog, a lot of this work was done at Argonne. So Dan Koritov is a student with us who led a lot of this work. Andrew Hirin, Yves Kovacs have done a huge amount of work as well. Patricia Larson and Joe Holloway have worked on the big lensing maps. I'll show you all of that. So this is how it looks like if you make an extragalactic catalog. You run GALSIM, which is an image simulation tool on it, and you forget that you have a telescope. This would be how LSST would look like if we would be out in space. There would be no atmosphere, no CCDs, so it's a pretty impressive picture. So we did that as part of getting ready for DC2.
Do you contaminate the stars?
This one, no. I'll show you. So in the end, so DC2 will have all of that stuff. So this one is just like a pretty. So we'll focus on this part of the simulation workflow. And so the first input is the n-body simulation. And that is actually something that I personally have worked on a lot. So at Argonne, we have developed this code called HAC, which stands for Hardware Accelerated Cosmology code. So the funny thing is that management at Argonne says the name is no good because HAC is not very serious. So they always call it HACC, which sounds really strange. It was really meant to be called HAC because it describes the code quite well. So we did a very big simulation on one of Argonne's supercomputers called Mira. The simulation is called the Outer Rim n-body simulation. It's a 3 GPC over H box with more than 1 trillion particles. So if you put it into comparison with the Millennium simulation, for example, the original one, it's like 260 times as much volume at the same resolution. So the mass resolution is around 2 × 10⁹. We overall generated more than 5 petabytes of data, so that's a lot. We have halo catalogs, merger trees, and light cone outputs, which you need in order to make a catalog that looks like SST. In addition, we have a small simulation. I will talk a little bit more about that. We called it Alpha Q. And so this is a 250 megaparsec box with 1 billion particles, so it has roughly the same mass resolution. And we mostly use it for prototyping, because honestly, if you have 5 petabytes of data sitting around, it's not an easy thing for students and postdocs or even staff members to work with.
It's totally independent on the Illustris TNAG 300, right?
It's what?
Nothing to do with Illustris?
It has nothing to do with, yeah. It's gravity only, so no gas. It's a totally different code, absolutely different. And it's much bigger. I mean, the last simulations are expensive because they have gas, so this is gravity only. So we started prototyping what we would do, how we would generate this extragalactic catalog. And our first idea was to use semi-analytic models. So semi-analytic models, what you do is you take into account the evolution history of each halo. So build these so-called merger trees where you see, okay, a halo comes together with other halos, gets bigger, it accretes mass. So you measure all these trees in simulation, you find time steps, And then what the semi-analytic model does is it runs physics-inspired models about galaxy formation in ODEs on top. So it does it in post-processing, so it's not as first principles as hydro simulations, but usually the alpha Q simulation, just to give you a couple of numbers, has roughly 4 million merger trees, and it took us 300,000 core hours to generate a Galacticus catalog. So Galacticus is a semi-analytic model developed by Andrew Benson. It's publicly available, so he helped us a lot with doing this. And we built a catalog, and results looked okay, but not great. So stellar mass functions, colors, they were all not quite right. I mean, but not quite right. So for example, if you want to run RedMapper, Eli will tell you the colors have to be perfect. Otherwise, RedMapper doesn't run. So I, as a simulator, would say, well, fix your code. But he says, no, fix your catalog. So we went with that. We fixed the catalog. The outer rim simulation has almost 2 billion merger trees. Galacticus, it would have been rather expensive. And we could have run it only once. It might not have been perfect. So we were not happy about that. And so that was the first time, and I was like, oh, what do we do now? We need this big catalog because LSST is big. And we have to come up with a solution. The solution, which was brilliant, was to hire Andrew Katrin, who is like a leading expert on the Halo galaxy connection. And he started then working with Dan and Eve and others on actually coming up with a new method, which is a hybrid of semi-analytic modeling and empirical modeling. And so we actually came up with something that instead of costing us 150 million hours is almost free. So it was nice. So how does it work? So this work took from start to finish roughly a year. So I should spend a little bit of time on the one slide that shows the work of 5 people for the better part of a year. So basically, what is empirical modeling is simply you measure properties of the halo, and from these properties like mass, and then from these properties you decide what kind of galaxy should live in it. And you can make this more or less complex. Like HODs are really just taking the halo mass into account. They're saying if you have a very big halo, then you have X galaxies in there. You distribute them with regard to the NFW profile, so on and so forth. You can have more complex models where you also say I take into account when a halo was born because that gives me information if a galaxy in there should be red or blue. But overall, what you basically try to do is you try to find halo properties that connect to observations, and then you tune your modeling parameters in order to get the I shouldn't work on that stuff, to get basically a really perfect map to observations. The problem is that it's predictive, and with LSST we will get into regimes where we don't have observations, so that's a little bit of a problem. So we don't really know. We can extrapolate the observations that we have right now to inform the model, but it's a little bit not so nice. That's, yep.
Sorry, do you need the halo mass function as input, or halo mass function as output?
It's the input.
It's the input.
Right.
So it depends what you use.
It's not the halo mass function, it's just the masses of the function, but you're right, it depends on the mass definition. And people just tune their model definition that you use. So that's relatively straightforward. So in our case, we actually used FOF masses. So the semi-analytic models, they really take into account structure, formation, history. They predict a range of galaxy properties using physics-based models, and they match observations really well. They're a little costly to run depending on the code which you're running. And what we basically wanted to do is take really the best of both worlds. So what you see here in this flow diagram is the following. So here you have the outer rim halo catalog and the catalog of the halos. And here on the right, you have an empirical model. This is based on the universe machine, which was done by Peter Baruzzi, Andrew Heron, I think Risa Wexler was on that paper, and some. So what they did was they took an extremely high mass resolution simulation, built an empirical model which is very well tuned to observations. So what we did was we said, okay, if a halo of a certain mass in this empirical model here will have certain properties. These properties that we took were stellar mass and the colors. That was all that we took. Then we said we find a similar halo in the outer rim simulation, and that's this Gull sampler pipeline blob, which is here in yellow. There. And we took whatever this empirical model told us this halo property should be, and put it into the halos into the big simulation. So now we have something that we call the base DC2 catalog. It has very limited properties, color, stellar mass, bright clustering properties, because we did start off with the real simulation. And now what we do is we take another library. So we used, I told you at the start, we took the alpha Q simulation, it's relatively small, and ran the full analytic model start to finish. So now we used that as a library of galaxies with a lot of different properties. So
Where cosmology enters this simulation?
Start in the outer rim. So I decided what the universe looks like. I decided the universe is WMAP 7, so it's not Planck, because I think Planck sigma 8 is just too low. So that goes into the initial. It's actually pretty insensitive though to cosmology. So it's not. It's actually. We are planning to do another one where we have a W0 WA cosmology. So the simulation is almost finished and all this machinery is set up. So that will be interesting to see if you can actually see differences. So after you have the base DC2 catalog. Right, you take the Galacticos properties of these galaxies, you match them up, and you build this extragalactic catalog, which is called Cosmo DC2. And this catalog has now a ton of galaxy properties. It has nice clustering properties. I'll show you a couple of pictures. The one thing that it still didn't have, even though the simulation is one of the two largest simulations in the world, the other one is the Euclid flagship simulation, which was done by Joachim Stadl and collaborators in Zurich, it still doesn't have enough resolution. So the problem is that supercomputers, while they are big, they don't have enough memory for us. And getting a mass resolution of 10 to the 8 that you would need for actually LSST kind of catalogs is not available in these very big volumes. So what we did was we populated the very, very faint end of the galaxy distribution. So we sprinkled in faint galaxies randomly into the field, and that actually works quite well. Catalog validation is very important. So what you see here is the halo mass range. And so we worked very closely together with analysis working groups to come up with a set of good validation tests. So we really wanted to make sure that our catalog was agreeing well with observations. And so you see here a range from SDSS deep to HSC data that we use to actually go over this full mass range to make sure that our catalog looked good. The one thing that we did for that was so it's a semi-automated workflow system, and that actually was part of that work in LSST DESC that helps you. So basically what DESQA allows you is it's a web interface. So you upload a catalog to NERSC, you hit a button more or less. The catalog is run through all these tests, and on the web interface you can take a look at the output. So you see if your catalog actually has the right properties. And this is a snapshot of DESQA at NERSC. And so besides the thing which says inspect, which means maybe there's something not so good, failed means that the code actually crashed. So this looks much better now. This was an old snapshot. But it's very easy. Now you can click, if you're on this web interface, on each of these buttons, and you get a picture of what the test looked like. So this is very useful. The other thing that was done as part of we developed a generalized catalog reader to make it really easy for everybody in the collaboration to access these catalogs. And the one thing that I will not talk about a lot, but that is also true, is that there are lots of catalogs in DC2. There's the Extragalactic catalog. There's a truth catalog, which has the stars, so we'll come to that. And then there is, for example, the COAD catalog, which has everything after DM processing was done. So all of this can be fed into DESQA now and being checked. Here, I showed you this before. This is a patch of DC2, this 300 square degrees in the south that we are actually simulating. And we have different catalogs right now available for the collaboration at different sizes. Just to make it easy to interact with the data, we put out a small catalog as well. As I said before, lots of quantities and that you can access in this catalog. And again, this catalog reader allows you to easily query what's actually in this catalog. There's something like 100 properties or so in there. Plots just about the validation. So here you see DN, DMAC. So this is in different bands, I and Z band. And so what you see here is we took HSC data and we did extrapolate it because HSC doesn't go out to this high magnitude. And so this blue line is how the catalog looks like. And so it's doing quite well. So the aim was to get up to 20%. And actually, it's right now, this plot is a tiny bit old. It's even better here in I band. So we made sure that actually this looks all good. And this thing that I said before, when we didn't have enough mass resolution to get the very dim guys right, that actually affected us up here. So to lift this up a little bit, we had to put in some dim galaxies by hand. This is NDZ. This is compared to data from Deep 2. The error bars are large because we did this test only on a small patch because it's actually a very relatively slow test. But again, you see we are matching the data pretty nicely. So this is in R band for different magnitudes again, and with respect to the rest. We have a ton of properties, as I said before, so ellipticity distribution, size distribution, so we made sure. And every time we went back, so somebody from an analysis working group was responsible for this plot, and we asked them, are you okay, even though, for example, this one might look not quite as good, and people said, yes, for LSST science, this is good enough. Something, again, that comes as part of Galacticus, so we get bulge and disk sizes, and so you can do a lot of things with this hybrid approach that you wouldn't have been able to do with just the empirical modeling easily. Black hole models, so you can do black holes. And what I will show you in the next couple of slides is that we also have AGNs in the catalog, so they had put in by hand. And so the AGNs were in part modeled taking these black hole properties into account. The other thing that is obviously very important, so G-Way becomes happy, is weak lensing. So we have weak lensing maps. Here is basically the workflow to make that happen. Again, this time you start off not with halos, but with particles. You take the particles, you make a nice light cone, you make density sheets, and then you ray trace through them, and make shear maps from that. So this was work that was led by our postdoc Patricia Larson, and again we did. You see the patch that we have. So that is actually already the 5,000 square degree patch. Decent resolution, and once you have this shear position in this catalog, the one thing that we did is you also have the galaxy positions, and you want to know the shear each galaxy position. So we took the shear field and we just interpolated it onto the positions of the galaxies, and that works pretty well. Tests look good. We have the mass surface density. I think Chive made this plot, or Francois, I'm not sure. So many people contributed to this, which is really nice, which makes it really nice. But so again, you see we are comparing here against SDSS data. This fall-off is because of resolution issues. It's totally understood because the density maps that we made had a certain resolution. And again, it was in coordination with the working groups that this was good. And here you see a similar plot that Chiwe showed you, real data. So that's the chi versus theta plot. So Cosmo DC2, it took us quite a bit of work. Was delivered, the very final version that goes into DC2 was delivered actually on November 28th in 2018. More validation tests have been done. Nothing came up that looked weird. RedMapper has been run on it. So we have heard about RedMapper this week quite a bit. It was successful, so Eli was happy with the red sequence. It was actually kind of funny when Elizabeth was yelling at your colleagues. So he and Andrew had some interesting interactions about the red sequence. Anyway, so that is all good. The catalog, the cluster catalog, is available for DESC members. And this Cosmo DC2 paper that is led by our student, Dan Koritov, is almost finished. So I personally want to release the catalog to the public, not just to DESC. So hopefully we'll manage with the paper to have this catalog come out so that everybody can look at it and play around with it. So then the next part is, so now we have this nice pristine catalog of galaxies. So the next part is that we also want the time domain science in the data challenge. And so this is something that was done by Scott Daniel, Bryce Kalmbach. Both of them are at the University of Washington. Bryce is a student who is almost finishing, looking soon for a postdoc. Biswas, who was a postdoc with us at Argonne and is now in Sweden, working with Hiranya Pyrus. This is part of the flow diagram that I showed you before that I'm going to talk for the next 5 minutes about. So what we want to do is we want to add additional transients and variables. So that is called SIM framework. So this was developed by the project, not by DESC, but we are happily using it, and actually we also improved it as part of DESC. And then after you have added these things, then you go on and do this Minion 1016 thing, where you really generate the exact seeing and everything. And I'm not going to talk about that, but that is kind of the next step in the workflow. So we have both galactic and extragalactic sources. So for the galactic sources, we have Milky Way sources. And this is from a simulation, from a GALFAST simulation from Urich et al. From 2008. It's stored in a database. And so what happens is that so you generate an instance catalog that has a specific part of the sky, and then this database is asking, like, what is the Milky Way, that part of that I would see if I point this telescope in that direction. And then it pulls out of the database the stars that belong to that. Then there are also galactic variable sources, M dwarfs, other stuff, so lots of things. I'm totally not an expert on this. And so all of this is put in so that we really have this contamination from the stars and everything. And maybe I shouldn't say that, but when we did the very first image simulation, it only had stars because we in a piece of the catalog that was not so good. And I was super, there's all stuff in there. And then Rachel Mandelbaum told me, those are stars, not galaxies. And I was like, oop. Okay, I go back to my theory studies, maybe. It was pretty embarrassing. Then for the extragalactic catalog, we have AGNs. Again, it's based on a model from McLeod et al. From 2010. So this is work, again, done by Scott Daniel. So AGNs are in there, so they are matched up to the galaxy. So he looks at what galaxy properties they are, and then he populates it with AGNs. And we have type 1a supernovae. So these are all over the wide, fast, deep region. And then in this deep drilling field region, there's a boost of that, so that we have more supernovae in there. And so this was, again, work done by Bryce and others. And so we have strongly lensed objects. They are only in the deep drilling field, AGNs, supernovae. So they are done with what's called sprinkler. And Phil Marshall also involved. Before he became spokesperson, and he actually had still time to do science, he was very much involved in this. So people are very excited in using this to do all kinds of interesting strong lensing and supernova cosmology science. So a couple of numbers and fun facts about this first part of DC2. So when we moved from Proto-DC2 to Cosmo DC2, we actually extended not only, we extended the catalog from Z of 1 to Z of 3, and we also included many more dim galaxies. And sometimes it's funny, so we should have expected that this catalog will be much bigger, but sometimes it's just like does things, and then one looks at what comes out, and, oh my goodness, this catalog is 10 times as big as the small catalog was. And some of our estimates of how much time it would take to do the image simulations were based on the smaller catalog. So we were like, now we have a factor of 10 to worry about. It's not good. Our image simulations become really, really expensive. In addition, the instance catalog generation, so I told you a little bit about this database access, that we would go at each part of the sky, ask what Milky Way sources are in there, grab them from a database and populate them in there. This database was living at U Washington, and universities often don't have very good infrastructure. The computer where the database was just gave up on us. Don't ask any questions, I'm tired. It literally died. I mean, they had to restart it. It literally died. So we were like, this is not good. and so this was at the beginning of September, and we were like ready to really start the big run. And so I had another of these moments where I thought like, oh no, this is terrible. But the one thing I must say is that everybody working on DC2 has been like really outstanding. And people like Scott Daniel, he worked day and night to fix this instance catalog problem. So one thing that we did was we moved the database actually to NERSC, where we produce the instance catalogs, and we duplicated it lots of times so that not the code would just query one database, but had lots of databases sitting around. So that helped a lot. He also sped up the code in other pieces. So one thing that I must say also is that physicists and astrophysicists are not very good in coding things efficiently. So we often code things, yeah, they work, and then we want to scale them up and everything falls apart. So Scott worked a lot on CATSIM, made major improvements. The IMSIM team also worked really, really hard. So IMSIM is one of the image simulation tools that we are using. And so when they saw that the image simulations got slower by a factor of 10, they just looked really hard at the code and identified where the weak points were in much more detail than they had before. And they actually were able to get this factor of 10 back. So that was really hard work by people working around the clock, and just so that I would be happy again. And I felt really bad because some of this, like, as I said, I was very much involved in the Cosmo DC2 part, but some of this was just me sending emails, please, 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 tell me that you found this factor of 10. So people probably got really annoyed by me, like, stop sending emails. So just a few interesting numbers, the numbers in these catalogs. So we have 2 times 10 to the 7 stars, we have 2 billion galaxies, we have 3 times 10 to the 7 AGNs. So what we did actually in the end was we made a cut with the galaxies at R, magnitude R of 29. We discussed this a lot with the analysis working group. It just seems silly, so we went out to R of 30 or something, simulate something that LSST will not be able to see. So everybody agreed we can make a cut to also get a little bit of this factor of 10 back. We have 6 times 10 to the 5 type 1a supernovae. And so the instance catalogs for DC2 are in full production. We have enough to simulate the first year. And it's chugging along. So that's really all good. So now the last part, in the last like 5 minutes, go over this quickly, is the image simulations and then the DM processing. It was a big team that came together to make this all happening. And this is the last piece of this workflow. So these are the image simulations, FOSIM and IMSIM, and this is the DM processing. So here's a snapshot from the image simulations. This one is actually after the DM stack was done. And so now here you should be able to see stars. So they are roundish objects. So everything is in there now.
So does it have DSF here?
Yeah, it does. So we have 2 image simulation tools. One is called FOSIM. It was developed by John Peterson at Purdue. It has a lot of physics, really complicated code. The other one is called IMSIM. IMSIM is based on GALSIM. So every weak lenser knows GALSIM actually. And so it was developed to have something that is a little bit faster than FOSIM. So it turns out that you can dial down accuracy in FOSIM to make it as fast as IMSIM. But it was just very nice because these codes are so complex to have two of them and to actually compare results against each other. The other thing that we did was we borrowed something from DESC. So this is a so-called exposure tracker. So what this thing does for you is, again, a web interface. And you can load up these images that come out of the simulations, and people can flip them and say, like, yeah, this looks good, this looks bad. And we actually did find, during the validation process, we found things that didn't look right. I have, like, my memory of what went wrong is gone. I remember how the pictures look like, but I don't remember why they were. We fixed it all, so all was good. The simulations, as I mentioned before, are rather costly. So they are running at NERSC, which is a center at Berkeley, and at Argonne. So ALCF stands for Argonne Leadership Computing Facility. And so this is me here. So we are actually, everything that's red here, even though they are different colors here, is us running on the supercomputer, which is actually a quite big computer. And this screen is in front of the director's office at Argonne, so he can actually see that we are doing a good job. Here you see again a focal plane from one of our simulations. I'm just so proud that it looks like LSST that I have to show these focal planes throughout the talk several times. One thing that took a lot of work also, and again, small teams were involved there, was to generate the workflows to make it all work together efficiently on these supercomputers. And so we used two different ones at Argonne, and actually for IMSIM and for FOSIM, and details connected to that. But again, it's good to have different tools to see what works best. This is just a picture. Again, this is one of these image simulations. It has been processed through already. And so this is kind of a summary what's all in there. So there are the galaxies for clustering and weak lensing, the AGNs, there are stars in there. So here's a beautiful star, right? Even I can identify that as a star. Then we have the time-varying objects in here, lensed AGN, supernovae. The PSF, you ask about it, its model. Atmospheric effects are in there. Optical distortions, so-called tree rings, which are like, the CCDs are not perfect. The dope is slightly irregular on the CCDs. Then you start seeing tree rings. And so you see them here. This is kind of another...
Like there is a kind of modulation in the background.
Yes, that's the tree rings, exactly. And so the DM stack has to take that out if it works correctly. So I guess this one was before we ran the DM stack, because they are still in there.
So the practice is very well fixed. Easy to
yes, in principle it's easy, but you have to be sure that you get it all. And it varies from CCD to CCD. It's not the same for each CCD, because it's really, when you make the CCD, you screw that up. And it's actually kind of interesting. The LSST has two different vendors for the CCDs. And one vendor has almost no tree rings, and the other one has many more tree rings. So it's not, you want to make sure you get it out.
You have planes?
Actually, we have here, you see there's a cosmic ray. So I don't think we have planes. We should probably put one in. The other very embarrassing story is that the first time when these tree rings were there, and somebody from Slack, who will not be named, and me, we looked at outputs from the image simulations before showing them to the experts, and we were saying, like, there's this weird pattern in there. And the Slack person said, maybe it's a PNG artifact, and just is. And then at some point we were like, oh no, these are really the tree rings. And we were like, yay, we got this right. So that's the thing, if you have simulators who simulate something which they have no idea about. Anyway, so there are also all these instrument signature features that have to be taken out by the DM. Vignetting, cosmic rays, we just looked at, crosstalk, all kinds of things that will be in the real data. Given the time, I'm not going to talk about the DM processing, but this is the full DM processing line. So take the image simulation, you pipe it through this. And the one thing that I want to say is INTP3 in Lyon is doing like a really heroic job, as well as people at SLAC on the NERSC machines to run this. And we had this small test run, which I said at the start was 25 square degrees. And the last processing with the DM stack has been done last week. And the data set was done in May. It's a small one. And it was just because so many things were found in the DM stack, either not set quite right or not working in the way that we understood it correctly. So running this DM stack is really a pain. This, since I only have like 2 minutes left, this is just an example of what kind of science you can do. So this is from François Lanous. And the one thing that you should just from this plot is, so this is real data, HSC, and this is the simulation after the DM stack. And what you should notice is this little blip here in blue, okay? This blip to blending. So what happened is that the DM stack, so here's a simulated image, and the DM stack actually thought that there's a galaxy here. It turns out that there is not a galaxy here, that this, which you, I mean, I can't even see this by eye, but this little schmutz here belongs to that big galaxy. And so the DM stack was not aggressive enough of taking these out. And so in HSC, they saw exactly this blip. And they redid the blending algorithm for the HSC data. They changed some parameters. And so when you do that and you run it again on the simulations, you see the blip goes away. So that's the orange curve. So François was very, very excited that the simulated data showed exactly the same feature as the real data. And we could show that the DM pipeline, that this is actually a really good test for the DM pipeline. So that was really nice. So the DC2 status, so run 1, as I said at the start, it's a smaller run, 25 square degrees out to the of 1. It's completely done. We have done it with IMSIM, FOSIM. We have run it through the DM stack, start to finish. The data products were released to the collaboration. In addition, we also have notebooks available which tell you how to access the data. Run 2, which is DC2, the instance catalogs are basically done. The cosmological catalog is done, and first IMSIM runs have been done, have been piped through DM, validated again, just to make sure we are not doing anything stupid, and more jobs are in the queue. The Cosmo DC2 catalog has been released to the collaboration, hopefully soon to the public. And we have something like 20 plus DC2 projects that have been announced already that want to use this data. What keeps us up at night still? One thing is really the DM processing. It's painful, it's slow, but I don't know how many in the audience of you know Robert Lupton. He is in charge of it, and I'm sure he'll fix it all. Really beautiful, but it is still something that is painful. The data access and serving the data is a question that we are asking ourselves. So we have implemented 3 different ways of doing this right now. And the question is, are they fast enough? Because as cosmologists, we want to access a large amount of data all at once to do our statistics. So that's something we are worried about. And data validation. So you can imagine this whole process is pretty complex from start to finish. So making sure that everything is right and we didn't screw up anything is super important. And so that welcomes new members, contribution to DC2. So to make sure that we all sleep well again, and while we are sleeping, we are actually dreaming of DC2 data, and this is again an image from our simulation. It doesn't come, it looks better on the screen, but a lot of stuff is going on, and hopefully a lot of science will come out of this. Thanks.
Yeah, so any questions?
Can you maybe comment a bit more on whether the galactic foregrounds, like for the CMB, like dust,
it's all in the
and so on. So they're included. That understood, but they're somewhat uncertain. So how big is their impact? Is it something that one?
That's a good question. So I can tell you one thing, which I didn't say during the talk. In one of the simulations, of the small simulations with FOSIM, it was actually forgotten to put the extinction because of the dust. It was a bug. And it actually is interesting because everything is much easier to observe, right? Because everything becomes much brighter. So we have seen a little bit of that, but we have not studied in detail if our dust model, if we tweak it slightly, what will happen. It is, for the extragalactic catalog, Andrew Benson and Andrew Herin are working quite a bit because you have both, right? You have the dust in the Milky Way as well as the dust in the galaxies. So they're working on the dust in the galaxies and trying to improve that model. So right now it's just taken from the literature. They think they can do much better than that.
Maybe if I can ask one more. So it seems to me that still there are like two stages in doing the simulation. One is producing really like merger trees and dark matter halos and everything, and then populating them with galaxies is the second step. So do you have an estimate like how important is the feedback that baryons would have on really matter clustering? Is there something to
so that's the interesting thing, right? So in the empirical approach, you match so that you get the data right, the observations. So in that sense, you have that in there when you do your modeling. You don't do it explicitly, but you do it implicitly by making your parameters look correctly, right? So it's not, you don't learn anything, right? Because you just generate something that looks like the real universe. I do think, though, that so LSST will be 10 years, and there will be for sure more matching of actual hydro simulations. That's something else that Andrew Herin in particular is interested in, is comparing hydrodynamic simulations to the semi-analytic methods, to the empirical models, and see if you can take some of this information from the hydrosims over to the modeling. But for this, it really doesn't matter.
Thanks.
More questions?
Hi, Katrin. It's really impressive. So I was wondering, what do you do for the intrinsic alignment, for example?
Well, that's a very good question. It's not in there right now, but they are working on it. So there are lots of projects that are going on right now that are like what they call add-on catalogs. So intrinsic alignments is one of them. And so they want to model it. Actually, nobody is. Are you involved in this? So François Lanous is one of the people who does it. So they want to use the actually the potential field from the particles as a first approximation. So that is maybe a little bit iffy, but they can also use the halo catalogs. So yeah, they are working on this quite hard right now to make that happen, but it's not in there yet. Yeah. I don't know. That's just me. That's just I have not thought about this that hard, but I would be surprised that it has enough resolution. But it might be. That's my only worry, that the resolution might not be good enough.
So what's the input data for the empirical simulation?
Sorry, what?
What's the data? The data used for the empirical catalog?
It's a lot. It's a lot. So that is in this. Well, so there are different things, right? So there is HSC data, SCSS data, Deep2 data, and then there's all the data sets that were used in the universe machine paper, which I can't even
and they all behave nicely and smooth. I mean, if there is no discontinuity in behaviors or properties.
Well, there are big error bars, right?
Okay.
I think that's one thing that the community will do over the next few years much more, to get better observations with smaller error bars and making sure that we can actually do this calibration much better. Right now, I don't know. I mean, again, I'm not an observer, but I would say the error bars are big enough that you wouldn't be able to really say there's something not consistent in the data, so if I'm using it for the modeling, it would be weird. Yes, so that's what's in the, I mean, the universe machine does do full MCMCs and optimization to get the modeling parameters, and then we just piggyback on that and use the results. But the data in that paper, I think we can always improve. So
that does make sense to later use LSST to feed it back and run.
Oh yeah, I would think so. But I think you really want some of these surveys that we have used, like Deep2, they are much smaller but much higher resolution. So it's a trade-off.
Okay, so let's thank Katrin again.